Let's talk about the second of two main topics in this chapter, solubility equilibria. For any solid that dissolves and dissociates in water, even if only to a very tiny extent, we can write an equation like the one here for calcium fluoride. The solid in equilibrium with the dissociated ions in aqueous solution. Since solids are left out of the equilibrium expression, we end up with an expression with the concentrations of the ions multiplied together, with each raised to the power of its stoichiometric coefficient. Just like an acid and base equilibria have their own designations, Ka and Kb respectively, these solubility equilibria are designated as the Ksp for the compound. We can write a generalized formula for Ksp expressions, with each ion in the formula's concentration multiplied together and raised to the power designated in the balanced chemical equation for that dissociation, which in turn is based on the compound formula. Let's consider an example problem. For any compound, if we know the concentrations of its ions in a saturated solution, one with the maximum amount of the solid dissolved at any given temperature, we can plug those values in to find the value for Ksp itself. For calcium fluoride, a saturated solution happens to contain 2.0 times 10 to the minus 4th molar calcium ions and 4.1 times 10 to the minus 4th molar fluoride ions. If we plug these into our expression and remember to square the fluoride concentration, and only the fluoride concentration, we arrive at a value of 3.4 times 10 to the minus 11, the Ksp value for calcium fluoride at 25 degrees Celsius. Since this is a very small value, you'd be correct if you predict that calcium fluoride doesn't dissolve all that much in water, since this is a reactant-favored reaction. The Ksp values for many compounds are known at 25 degrees Celsius and would be provided for you when needed. Some examples can be seen here. Another example, if we know the Ksp value for magnesium fluoride, we can find its molar solubility in water at 25 degrees Celsius. When MgF2 dissolves and dissociates, it produces 1 molar equivalent of magnesium 2 plus ions and 2 molar equivalents of fluoride ions, as seen in the balanced chemical equation here. Since pure water contains neither of these ions, they have initial concentrations of 0, and due to the stoichiometry, we add values of x and 2x respectively for magnesium and fluoride concentrations to reach their equilibrium levels. Plugging in these expressions into Ksp, we get x times 2x quantity squared, or x times 4x squared, or 4x cubed. With the numerical value for Ksp provided as 7.4 times 10 to the minus 11, we solve for x by dividing both sides by 4 and then subsequently taking the cube root, which gives us an x value of 2.6 times 10 to the minus 4 molar. This is the magnesium ion concentration, and since that's formed in a 1-to-1 molar ratio with the reactant solid, this is the molar solubility of magnesium fluoride as well. The common ion effect applies to solubility equilibria too. Consider this example. We just found the molar solubility of MgF2 in pure water, but what is its molar solubility in a 0.10 molar sodium fluoride solution at the same temperature? Since the solution already contains 0.10 molar concentration of fluoride ions, our equilibrium concentration of those ions will not be 0 plus 2x, but 0.10 plus 2x. Plugging this in for fluoride concentration and x for magnesium concentration gives us the result shown here. Like with weak acid or weak base equilibria, we can assume that x is very small compared to our initial concentrations, so 0.10 plus 2x is effectively still just 0.10 after rounding. Making this simplifying assumption, the x value we get is 7.4 times 10 to the minus 9 molar. Comparing this to the result in the previous problem, we can see that the molar solubility of MgF2 in a 0.10 molar sodium fluoride solution is several thousand times lower than its solubility in pure water, and the difference is due to the common ion effect, which is just a specific case of Le Chatelier's principle at work. We can also see the common ion effect in action in a similar fashion to its impact on buffer solutions. As the sodium fluoride concentration of a solution increases, the lower the molar solubility of MgF2 will be due to the common fluoride ions that they both contain. Let's consider some other factors though. For many ionic compounds, the pH of a solution will affect its solubility. For instance, consider calcium carbonate. This is a mostly insoluble solid, but like any compound containing carbonate ions, it reacts with hydronium ions in solution as shown here. Since lowering the pH corresponds to increasing hydronium ion concentration, we would predict, based on Le Chatelier's principle, that the equilibrium should shift towards the products, in other words, the dissociated ions, if the pH is more acidic. And as you see here, the molar solubility of CaCO3 increases as the pH lowers or becomes more acidic. Let's look at another phenomenon that affects solubility, complex ion formation. Many metal cations are capable of reacting with certain Lewis bases to form what are called complex ions. For instance, silver ions can react with the Lewis base ammonia to form the complex ion in the first step, and this can further react with another ammonia equivalent to form a complex ion with 2 ammonias for every 1 silver. The net result is shown in the equation at the bottom. Notice that the formation constant for each individual step is relatively product favored, and the formation constant for the overall process is actually extremely product favored. Like with any process where we add 2 equilibrium reactions together to get an overall equation, the equilibrium constant for this overall process is equal to the product of each step's individual equilibrium constant. Since each step in the formation of the silver ammonia complex is already quite reactant favored, the overall process has a huge formation constant, so the process is overall extremely favorable. The example here shows how this complex ion formation can affect solubility equilibria. For instance, AgCl, silver chloride, is extremely insoluble in water. Its KSP value is something on the order of 10 to the minus 10. However, if we take solid silver chloride and add an excess of aqueous ammonia to it, we can see that it dissolves quite readily. Since the silver ions form a complex with the ammonia effectively removes the silver ions from the silver chloride solubility equilibrium. Since we're eliminating one of the products, the equilibrium for the dissociation of AgCl shifts towards the products, in other words, away from the solid and towards the dissociated ions. Plotting ammonia concentration versus molar solubility of AgCl shows this effect in action. The complex ion formation is responsible for the increased solubility of AgCl in ammonia solutions versus its extremely low solubility in just pure water. Let's look at one more factor to consider with regards to solubility, amphoterism. As an example, we'll consider aluminum hydroxide. Like most hydroxide compounds other than the strong bases, aluminum hydroxide is quite insoluble in water. Since hydroxide ions are strongly basic, it might not be surprising that this compound is more soluble in strongly acidic solutions than in pure water. The acid reacts with hydroxide ions, removing them from the equilibrium and causing the dissociation to proceed towards the products, away from the solid in the KSP expression. What's stranger, though, is that aluminum hydroxide is also quite soluble in strongly basic solutions. In a strongly basic solution, of course, we have high concentration of hydroxide ions, so shouldn't the common ion effect mean that the aluminum hydroxide should be less soluble than in pure water? That's what you'd probably think, based on everything we've discussed so far, but adding excess aqueous sodium hydroxide, for instance, to the white solid aluminum hydroxide actually causes it to dissolve. This is because aluminum hydroxide is amphoteric, meaning it can react with both acids and bases. In particular, with bases it forms the complex ion whose formula is shown on this slide, Al (OH) close parentheses 4 with a -1 charge. This is essentially a type of complex ion formation that removes aluminum ions from the product side of the dissociation equation. Taking this behavior into account, we get this strange graph where instead of there being a simple relationship between pH and solubility, aluminum hydroxide is essentially insoluble between pH 4 and pH 10, but has high solubility both below pH 4 and above pH 10. Like with any equilibrium, we can predict the direction that a mixture of dissociated ions will proceed in to establish equilibrium by analyzing the reaction quotient for a given set of conditions. Just a quick reminder, a reaction quotient is the same expression as the reaction's equilibrium constant expression, but with arbitrary values plugged in for each concentration instead of equilibrium values. For solubility equilibria, the reaction quotient is also called the ion product, for fairly obvious reasons. The interpretation of the ion product is relatively straightforward if you recall the relationship between K and Q from chapter 15. If the ion product Q is greater than KSP, the solution has more products than at equilibrium, so the solution is supersaturated and will have to shift to the left to establish equilibrium. Since the left side of the equation is the solid, that means that precipitation will occur. If the ion product is equal to Ksp, the solution is already at equilibrium, meaning that it's saturated. It contains the maximum possible amount of that compound dissolved at the temperature in question. And of course, if the ion product is less than Ksp, we have less products present than at equilibrium, so the solution is unsaturated and no precipitation will occur. Calculating the ion product, then, can be used to predict whether a given concentration of ions will produce a precipitate or not. That's going to be a wrap on Chapter 17. We're not going to go any further to cover ion separation by selective precipitation, for instance, so you can ignore those sections in the textbook. Thank you for your time and attention, and please continue to stay safe out there.